are contained in second kind, and the differential of second kind are obviously contained in the differential of third kind. Now we will see which kind of differential we have on an elliptic curve. On an elliptic curve defined over C, we have has differential of first kind. We have ax over y, omega, it's a classical notation of this differential of first kind, and the pullback via the exponential map of this differential of curve first kind, it is just dz. Has differential of second kind, we have eta, which is x, dx over y. It has a double pole with residue 0 at each point of the lattice, and the pullback via the exponential of eta is just p dz. These two differentials are well known. Nothing is new now. What is, according to me, not so well known are the differential of third kind. The differential of third kind that we write CQ is 1 over 2 y minus y of q over x minus x of q dx over y. For q is varying on the elliptic curve, is a C rational point on the elliptic curve different from 0 and also from any torsion point. What is interesting for us is that this differential of third kind has a residue divisor equal to minus 0 plus minus q. So we have an infinity of differential of third kind parameterized by the point of the elliptic curve. The first two differential are well known. This one is something new. Now I want to make the link between elliptic integral and periods. So if q is any elliptic logarithm of point q, what is an elliptic logarithm? It's just that exponential of small q is pq. We have that the pullback via the exponential map of this differential form of third kind is 1.5 p prime z minus p prime q over pz minus pq dz, which has residue minus 1 at 0. Now we want to make the link with period. So I take gamma 1, gamma 2 a basis of the lattice. It has rank 2, I recall. And we have that, this is a very classical result, elliptic integral of the first kind. This is the integral of omega along gamma e are the period of the Weierstrass P function. This means that P of z plus omega I is equal to P of z. The Weierstrass P function is periodic, is omega I periodic. Now, the elliptic integral of second kind, that's mean the integral of the eta along the gamma I, are the quasi-period of the Weierstrass zeta function. This means that zeta of z plus omega I is equal to zeta z plus omega I. And these are well-known results. Huh? In his course, PECO at the Collège de France, Michel Waldschmidt observed that there was no function whose quasi-period are elliptic integral of the third kind. That means elliptic integral until this date never appear as a period of a function. a solution was found by Serre, which proposed the following function, fqz equal to sigma z plus q over sigma z sigma q multiplied by e to the minus theta qz for any small q in C minus the lattice. So this function of Serre is you can define such a function for any point of the elliptic curve, which is not a torsion point. So this function has a very nice property. The logarithmic differential of this function, that is f prime qz over f qz dz, is exactly the pullback of CQ by the exponential map. And moreover, the exponential of the elliptic integral of the third kind, that is, so first we do the integral of the CQ along the gamma e, which is equal to eta e q minus omega e theta q. And then I have to take the exponential of this integral. So this number are the quasi period of the function fqz. This means that fq variated in z plus omega I is equal to fqz multiplied by exponential of eta iq minus omega I zeta q. So in this case, with the elliptic integral of third kind are not really period, but I have to take the exponential. This is the difference with the elliptic integral of the first and the second kind. So perhaps now it's a good time to make a small break if you have any question until now.
Sorry, what exactly the question, the claim was that there are no such functions and Serre produced an example. Is that what you're saying?
Yes, yes. We know that here, we know that elliptic integral appears as a period of the Weierstrass P function. The elliptic integral of a second kind appear also as a kind of period of a function, but the elliptic integral third kind was a period of nothing, and Serre introduced this function which has the property that it is a kind of period for this function fqz.
Great, thanks.
So now I want to go on. I want to introduce semi-abelian variety. So semi-abelian variety are extension of abelian variety by tori. In this talk, I will speak only about elliptic curve, and for us, the tori are just the multiplicative group, GM. So a semi-abelian variety is an extension of our elliptic curve by GM. And via the isomorphism between the dual elliptic curve and the X1 EGM, we have that any extension of E by GM is parameterized by a point of E dual or by a divisor of peak zero of E. But since, and so our extension G of E by GM is in fact correspond to a point Q of E star or to a divisor D equal minus Q minus zero of peak zero of A. And here you can make the link with the divisor of the elliptic logarithmic differential of Serre function. this will be the link that we will see now. The RAM homology of such an extension has basis omega, this is the x over y, and eta, x, the x over y, which we see that these two are the basis of the RAM homology of an elliptic curve. And then we just add this CQ, which is related to the differential of third kind. And the residue divisor of CQ is exactly the divisor who parameterizes the extension G. And this is so the basis of the RAM homology of G, of such an extension. The path of G, or here there is a min stack, instead of path on M, one should read a path on G. A basis for H1 G of Z, we take gamma 1, gamma 2, which are basis of loop in the elliptic curve. And then we take delta Q, where delta Q is a path around the point Q, minus Q. And Q is always the point which parameterizes the extension G. Now I need the definition of one motif. I will give it for an algebraically closed subfield of C, which is not necessarily algebraic. So any subfield of C is fine. So one motif is an object like this, M equal to a length one complex. So it is just an arrow from Z to the R to a semi-abelian varieties, to our extension of E by GM. And everything should be defined over K. So we have that G is an extension of an abelian variety by a torus in general, but for us, the abelian variety is just the elliptic curve, and the torus is just Cm. And we then take a morphism of group from Z to the R to G. And in order to make things more easy, we will take R equal to 1. So this morphism, group morphism, is just to fix a point on the extension G. So you take an extension of E by GM, and you choose a point on the extension, a rational point on the extension. You can define one motif in a more general context above any scheme, but for us, the definition over K is enough. One motif has been introduced by Deligne, and so I want to recall now this construction. So yeah, there is a morphism between the dual elliptic curve and X1 EGM. We have already observed that the extension of E by GM is equivalent to have a point in A star, or to have a divisor on peak 0 of A. We have already observed this. By a result of Mumford, to have a rational point on G, it is equivalent to have a point P on the elliptic curve, a rational point P on the elliptic curve, which will be the projection of R in the elliptic curve, because we have the projection G on E. And the rational function G is a rational function such that the translate by P of the divisor minus such divisor will be minus Q plus P minus Q plus 0. So to have a point R in the semi-abelian variety is just to fix a point in the abelian variety and this rational function. in order to starting from the elliptic curve, in order to get really one motif, we have in some sense to torture the elliptic curve in the following way. This was the original construction of Deligne. We have first to pinch the elliptic curve at 2 points, minus q and 0, and then to puncture the elliptic curve at 2 rational points, P2 and P1, whose difference, according to the group law of the elliptic curve, is the point P. This is the original construction of one motif given by Deligne in Théorie de Hodge 3. So for the construction of one motif are a mixed motif. That means that they have a weight fluctuation, which is not trivial, but as we have, as you can observe, one motif are constructed starting from an elliptic curve, a torus, and Z. So in the cohomology of one motif, you should recognize also the cohomology of the elliptic curve, the cohomology of the torus, and the cohomology of Z. And in fact, you can devisate the Hodge cohomology and the Durham cohomology of the one motif in the following exact sequence. So TH of M is the Hodge cohomology of M. This is the Q vector space generated by the loops. And it is an extension of Z tensor Q by the space of loops of G. And the space of loops of G is an extension of the space of loops of the elliptic curve by the space of loops of GM. So you can, in general, in any construction that you do with one motif, you can devisate, you can split this construction using the analog construction for the torus, for the elliptic curve, for the semi-abelian variety, and for Z. For the Durham cohomology, for the differential form, we can do the analog construction. So the vector space of differential form of M is an extension of the vector space of differential form of G by the vector space of differential form of Z. And this extension here is split. And the H1 Durham of G is an extension of H1 Durham of GM by H1 Durham of E. This, we will use this in order to find a basis of path on M and the basis of differential form on M. And this is what we will do now. We consider one motif. So I recall it is just a semi-abelian variety and the point on it. So we have G, which is an extension of our abelian elliptic curve by GM, and the point R on it, leaving above P. P that we see as P2 minus P1. Semi-abelian logarithm of R, it is just a couple because Li of G is isomorphic to C2, and L and P are 2 points of C2 such that exponential of LP is equal to R. So as basis of differential form on M, I choose omega the differential form on the elliptic curve of first, second kind. Then we have zeta q, the exponential, the differential form of third kind on the elliptic curve. And then I have only to add df, where f is a rational function, such that this is a kind of normalization that we will need later. Fp2 minus fp1 is equal to 1. This is for the differential form. For the path, I choose gamma 1, gamma 2. It is gamma 1 tilde, gamma 2 tilde are essentially the pullback of gamma 1, gamma 2 via the exact sequence that we have seen before. Then I take delta Q, a closed path around minus Q, and beta R, a path from 0 to R on G. Now I have a basis for the differential form of M and the basis of map on loops on M, sorry, that we have constructed. And perhaps this is the good time to make question, because now I will speak about the Grothendieck conjecture of one motive. If you have a question.
Sorry, can you see again what the point R was? Q corresponds to the extension. Q gives rise to the extension.
Q corresponds to extension, and the point R is living in G. And since G is an extension of E, the elliptic curve by GM, this point R live above P. Perhaps I'm going in the wrong direction. This is the construction of Mumford, but it is more complicated according to me. The point R that you need to define if you want to have a one motive is equivalent to have a point P on the elliptic curve, such that the projection of G in A via this surjection that you have, because G is an extension of A by GM, it is the projection of R is just P.
Thank you.
It is the point that you need that appear in the definition of the one motive. A one motive is an extension of an elliptic curve by GM, and then you need a morphism U, which this morphism U correspond to a point R on G, because U of one is the generator of R, is our R.
Excellent, thank you.
So Deligne show this is a general fact. It is not true only for one motive. It is true for a projective variety in general. But Deligne showed that in the case of one motive, the integration of differential forms give a canonical isomorphism between the C vector space of differential form on M and the dual of the space of loop, and to each differential form you associate the map to any loop. Any loop is sent to the integral of this differential form along this loop gamma. This is a general fact, which is true for any projective variety, but Deligne proved this isomorphism also in the case of one motive. A period of a one motive are exactly the coefficients of a matrix which represent this isomorphism with respect to K bases. So the period are just the matrix of this isomorphism. This is true for any, this is true in general. The period of an elliptic curve are the coefficient of a matrix which represent the above isomorphism with respect to K bases. This definition is not only for one motive, this is for in general for projective variety. So in our case, with the basis that we have chosen, the matrix of period of M is the following one. We have the integral along beta R of Tf. The first line are all the integral along beta R. Beta R was the path from 0 to R. And you compute the integral along this path with all the differential form that we have, df, omega, eta, and xq. Then we have to integrate along gamma 1 omega a times CQ, along gamma 2 omega a times CQ, and we integrate along delta Q CQ. In the first column and in the last row, we have a lot of zero. This is because one of the exact sequence that I have showed to you was split. So this is due to the fact that the cohomology in some cases really split. So the period of them are all these integral. So we can compute explicitly because all the integral which appear here are quite easy to compute. What is quite new is the integral along beta r of CQ. And CQ, the pullback of CQ by the exponential is dw and f prime q over fq dz. So I have to integrate the first d omega from 0 to L and this logarithm differential from P1 to P2. And I recall that P1 minus P2 was the point P. And this I get L plus log FQ P2 over FQ P1. And I can write it exactly as L prime plus log FQP using the following addition formula of cell function applied to P plus P1 is equal to P2. So I reduce this period to L prime plus log FQP. I recall that small p is the logarithm of the point Q which parameterizes the extension G, and small p is the logarithm of big P, which is the point on the elliptic curve above which lives the point R, which define over our one motif. Now, explicitly, if we compute all other integral, in fact, are written in the literature, so they are not new. So the period of MR1, P, theta P, L prime plus log FQP, omega 1, eta 1, omega 2, eta 2, which are very famous period, eta 1 Q minus omega 1 CQ, eta 2 Q minus omega 2 CQ, and 2 pi I. 2 pi I, in fact, are the period of GM. And omega 1, eta 1, omega 2, eta 2 are the period of the elliptic curve. So the period of M are composed by the period of the elliptic curve, which are well known, the period of the torus, which are well known, and I have to add the period related to the point P, the period related to the point Q, which parameterizes the extension, and the period related to the point R. Now I want to speak about the conjecture of period, but perhaps now it's good to make a question if you have question.
Sorry, I have another question, and I want to encourage other people to ask questions too. So can I summarize the discussion at the beginning to say that you've given a geometric explanation of geometric explanation for these elliptic integrals of third kind. So you're showing us how to go look for these by constructing this geometric object one motive whose periods are exactly elliptic integrals of third kind.
Yes,
right?
yes, okay. Yes. And exactly here, this column are in this column, you see that you need the elliptic integral of third kind. Elliptic integral of third kind appear as period of one motif. If you just consider elliptic curve or tori, you have just elliptic integral of first kind, which give you omega 1, omega 2, elliptic integral of second kind, eta 1, eta 2. And then if you, in order to make elliptic integral of third kind to appear, you need to speak about one motif.
And was this what Serre did?
Sorry?
I didn't mean to interrupt you. Is this what Serre did? Was this what he was thinking behind the scenes when he came up with this function? Or
no, I think that Serre just want to answer Michel Waldschmidt question, but in fact, answering this question, he indirectly give this interpretation of elliptic integral of third kind.
Okay, so he didn't write it out explicitly, but people.
No. What is written? No, Serre just answered the Michel Waldschmidt question. All what's come after. It was done essentially by Daniel Bertrand, okay. And until here is done by Daniel Bertrand, all this computation in the case of elliptic curve, and now my job starts.
Okay, awesome, really cool.
Okay, go on. Now we want to speak about conjecture of period. So, Grothendieck conjectured that any polynomial relation with rational coefficient, okay, between period of an abelian variety should have a geometrical origin. But he never explained mathematically what this means. He just gave this this intuitive explanation. Long then reformulate this, saying that this means that the existence of algebraic cycle on A and on the product of an abelian variety with itself should affect the transcendence degree of the field generated by the period of an abelian variety. So you take a field generated by the period of A, the transcendence degree of this field should decrease if you show that it exists algebraic cycle on A. More algebraic cycle on A you have, more this transcendence degree should become small. So then Deligne never write down, Grothendieck never write down an explicit conjecture. This was done by essentially Yves André, which generalized this in the case of one motif. And he said that if M is, it does it for any motif, just for one motif. But for us, it is important one motif. The transcendence degree over K generated by the period of M is bigger or equal to the dimension of the motivic Galois group of M. The motivic Galois group of M is a very complicated group, but he has his role is to fix algebraic cycle. In the case of one motif, the motivic Galois group is really isomorphic to the Montfort-Tate group, and perhaps the Montfort-Tate group is more well known as group. So what is important here is that the transcendence degree of the period of M is really related to the dimension of group scheme, which is related to the presence of algebraic cycle on M. In fact, the first conjecture of Grothendieck was only for abelian variety defined over Q bar. And he said that the transcendence degree of the field generated by the period of A is equal to the dimension of this motivic Galois group. Then Yves André generalized it to a more general geometrical object has one motif. And if the field is not algebraically closed, you don't have equality in this conjecture, but you just have that the transcendence degree is bigger or equal to the dimension of the Montfort-Tate group or to the motivic Galois group. I don't want to define this group because it's really complicated. I will just give some detail later. K is the field of definition of our one mode. If we can assume K to be Q, G2, G3, P, Q, R. So this is the field of definition of our one motive. So there is a more symmetric definition of one motive. So I recall that one motive, so it is an extension of E by GM, and then we fix a point R on G, whose projection on the elliptic curve is our P. So as we have seen, the extension G is parameterized by a point Q. And so in fact, this point Q is just an arrow from Z to E star, whose this map is sent just one in Q. So to have Q is the same thing as to have V star. To have the point P is the same thing as to have an arrow V from Z to E, so that V of 1 is P. To have the point R, we have another interpretation of the point R. This point R corresponds to a trivialization via the pullback by V and V star of the Poincare-Hébie extension of E star by GM. A point R is given just by the image of this trivialization C11. This is due to the fact that if you restrict the Poincare-Hébie extension above E cross Q, and this is exactly G. And then if you want to fix a point above P, you just need a point above the fiber of the Poincare-Hébie extension above PQ. So if we consider our one motive, now we have computed the period. So explicitly, we can, in our case, quaternion period conjecture becomes the transcendence degree over Q. Then I put G2, G3, PQR because they belong to the field of definition of the one motive. And then I add all the period, 2 pi I, P, zeta P, eta 1 Q my omega 1 zeta Q, eta 2 Q minus omega 2 zeta Q, L prime plus log FQP. All this number was the period of M. And this is bigger or equal to the dimension of the motivic Galois group of M. And this is equal to the dimension of the Galois group, dimension of the motivic Galois group of the elliptic curve, plus the dimension of the unipotent radical of the motivic Galois group of M. And in fact, the Lie algebra of this unipotent radical is an extension of B by T, where B is the smallest abelian subvariety of A cross A dual containing PQ, and T is a smallest subtorus of GM containing the trivialization which give you the point R, and the image of the couple PQ by the Weil pairing. Obviously, in our case, the dimension of B can be 0 if PQ are torsion point, or can be 1 if PQ are endomorphism of E linearly dependent, or it can be at maximum 2 if PQ are linearly independent. The torus T can have a maximum dimension 1 or 0. In this table, I summarize all the dimensions that can have the unipotent radical of M, and the dimension of the morphotate group of M, depending if the elliptic curve is CM or not CM. So if you see if P, if QR and so P are torsion, the unipotent radical has dimension 0, and the molecular group can be 2 or 3. Here I just summarize the more easy and interesting case geometrically. Then I want to show you how the conjecture reduce in some of these cases. I don't know how time I have yet, perhaps 5 minutes. Example of conjecture in the case R and Q are torsion. So in this case, I recall that Q was the point parameterized the extension G. If Q is torsion, I work modulo isogeny. So I can suppose Q is equal to 0. And my extension is parameterized by 0. This means that the extension G is trivial. It is just the product of the elliptic curve by GM. If R is torsion, we have that the point R is modulo isogeny is 1. If R is torsion, also P is torsion, and P is 0 modulo isogeny. So I have that if A is not CM, using the table that I showed in the last slide, for at least of the 6 numbers G2, G3, omega 1, omega 2, eta 1, eta 2 are algebraically independent over Q. If E is CM, so 2 at least of the 4 numbers G2, G3, omega 1, omega 2 are algebraically independent over Q. If the elliptic curve is defined over Q bar, this means G2, G3 are algebraic. This reduces to the Chudnovsky theorem. This means that transcendent degree over Q of the field generated by omega 1, omega 2 is exactly 2. And this is the only case where the Grothendieck period conjecture is no. This is the case just of an elliptic curve of CM type defined over Q bar. So this conjecture is really very difficult because since several years, no progress was done. Then, for example, if I choose P and Q torsion, I reduce to this case that I have studied in my PhD thesis. So Q torsion, this means that the extension G is trivial. So I have again the case A cross GM. And P is torsion. The point above which leave the point R is torsion. But this means just that I can choose R living in GM, and this time R is not torsion. So if A is not GM, 5 at least of the 8 number, G2, G3, omega 1, omega 2, eta 1, eta 2, R log R are algebraically independent over Q. This log R is really the usual logarithm because big R live in GM. So it is the log, the inverse map of the classical exponential. If A is not CM, 3 out of the 6 number, G2, G3, omega 1, eta 1, R log R are algebraically independent over R. So I can show you, I have prepared also the other case that we can perhaps show this last slide. You can do all the case that you want, P torsion, Q not torsion, R torsion. So, we work, if R is torsion, G is not split in this case. So we have really an extension. And so if A is not CM, 6 at last of the 9 number, G2, G3, omega 1, omega 2, eta 1, eta 2, Q, zeta Q are algebraically independent over Q. And if E is CM, I have that for a last of the 7 number, G2, G3, omega 1, omega 2, Q, CQ are algebraically independent over Q. So starting from the Grothendieck period conjecture, you can get a lot of other small conjecture, choosing adequately the parameter P, Q, R, which define the one motive. So I have done all the cases, but I think it's quite boring to see all these cases. I want to finish here my talk, and I want to thank everybody. Thanks.
And
I have virtual.
In the participants tab, you can use that to clap or type in chat.
Okay.
Many ways to do a beautiful job.
I hope there are no eggs that you can throw. So I can quit the sharing.
Yeah, unless there are questions.
Or if you need again.
Are there any questions? Is Frank here?
Yeah, I'm here.
Oh, sorry, I used to go. I have some questions. So I'm muting myself. I hope like other people have questions to ask too. I don't want to be taking over all the question time. So one question I had, like all that big table you had with different possibilities for PQ and R. I think the most generic case would be when all of them are not torsion, right? That was not.
Yeah. Yes.
So we know.
No, I just do very easy example. If PQ are end of E, where end of E are the endomorphism of elliptic curve, are end of E linearly independent, maximal dimension is 7 or 9. But geometrically, you have always the one motive ZG, and so I didn't put in the table this case. I just do the case where P, Q are torsion, because so you can see more geometrically what happens. Okay. But sure, they are not all the cases, yes.
Okay, and do we have, so we can think of perturbing these points around, PQR around. Do we know how the dimension of this motivic group jumps? Like what kind of loci does it? Generically, it's some value when it goes up or down. Like you have these two pieces. Should you study them separately? How should I be thinking about this?
Oh, the two pieces, you mean B, the abelian variety generated by PQ, and then the torus. So the dimension of the motivic Galois group is related to the dimension of an abelian subvariety of E cross E star, and this we know very well because if subvariety of abelian variety, if the point are torsion or the point can be endomorphism linearly dependent or not dependent. So this part is well known. The part of the torus is much more complicated, and I still studying it because I don't understand it very well yet. So I understand very well the link between P, Q, but not the point R above which the point R living over P. This part is more difficult. I don't understand 100% yet. So this is a work in progress.
Thank you.
I have one question. Can you say anything about Jacobians of higher genus curves, and in particular integrating differentials of, or the periods of integrals of differentials of the third kind there?
No, I don't have studied this yet, but I think it's something that I can do in the future. I just studying third kind elliptic integral for elliptic curve. So, but this is a good question and perhaps a good idea for the future.
Anything else? Okay, well, let's virtually thank Cristiana again for a wonderful talk. Let's see, so we have a coffee break, and we have a short break before the break. So maybe a future version of Zoom, you can provide coffee through the computer, but we haven't gotten that far yet. So please, let me encourage you to get some coffee. If you don't want to do the social breakout rooms, I'd encourage you to log out for now and come back at 10:40 for the contributed talks. And Padma, maybe you'd like to say more?
Yeah, so if anyone wants to specifically request, Cristiana, are you around for the coffee break?
Yes, I'm here.
Yeah. So if anyone specifically